Hi everyone! So in today's video, we're going to learn a new derivative rule that's called the chain rule. So we'll get there in a little bit, but basically kind of big picture what's going on. So far we've learned a variety of derivative rules that kind of work independently. So we've learned the power rule for taking derivatives of x to a power. We've learned how to take the derivative of a constant, just a number. And we've learned how to take the derivative of trigonometric functions. And then we learned the product and quotient rule. And so those rules are a little bit different because they're not really a rule that's for one specific type of function. They're a rule that works to take the derivative of different types of functions put together in different ways, right? So we had, like, if you have two different types of functions multiplied together, you use the product rule. If you have two different types of functions being divided, you use the quotient rule. And so the chain rule is going to be a lot like that. And it's going to help us take derivatives of functions that we will call composite functions. So we'll get there in a little bit. So before we get into what the chain rule is, I want to kind of pose a question that will, just sort of give a sense of what type of thing we're talking about here. So my question is, what is the difference between, I'm going to give you two different functions. And then I'm also going to ask you, which of those two functions do we know how to take the derivative of? Oops. Sorry, the screen is kind of stuck. There we go. Okay. Which one do we know how to, and I'll just say differentiate, right? So differentiate is the verb form. It's basically a one-word way of saying take the derivative. So the first function is going to be h of x is equal to x squared times sine of x. And then the second function is going to be h of x is equal to sine of x squared. So think about this for a moment. You can pause the video if you want. Think about how you would describe to someone what is different about these two different functions. Because I think understanding and being able to describe what's different between these two functions is going to be really, really fundamental in you succeeding in this section. Okay, so what is the difference here? Well, what I would say is that the first one is a product of two different functions, right? So this one is a product of two functions. Sorry, I don't know why my screen is not behaving well right now. Specifically, it's the product of the functions f of x is equal to x squared and g of x is equal to sine of x, right? Like if you read this function out loud to someone, you would say x squared times sine of x, meaning that it's a product. You're multiplying two things together. And so what does that mean? That means that we can take the derivative of this using the product rule. So we can, and I'm not going to actually do it. Hopefully you remember that from last week. But we know how to differentiate this type of function. Oops, I was about to write quotient rule. That's not right. Product rule. Okay, so what about this second function? So what's different about this? So is this one a product of two functions? And the answer is no, right? Like I would challenge you, if you think it looks like it's a product, what are the two functions that are getting multiplied? There's no two functions that you could define that are getting multiplied to give you this function overall. You might say like sine and x squared, but if you think about it, sine on its own doesn't really mean anything. Sine needs to have an input. So this is not a product. This function is what is called a composite function. And we'll get into that, what that means in a moment. But a composite function, roughly speaking, basically means that you have one function that is plugged into another function. So whereas in the other one, we had kind of two like basic functions, x squared and sine of x, and we just kind of stuck them together and multiplied them. in this case, we're taking x squared and we're plugging it into sine of x. And so that is what's called a composite function. It's like a function within a function. And so basically, we do not yet know how to take the derivative of this. That's what we're going to get to today. We're going to use something that's called the chain rule to take derivatives of functions that look like this. So we do not yet know how to differentiate this. But that's what we're going to talk about today. Okay, so I want to start, before we even get into derivatives, we're going to spend a little bit of time just talking about what it means for a function to be a composite function and practicing with identifying what are the two functions that are being composed. So this is review from 141, but I want to really refresh your memory on it because it's really important in order to, like, basically if you can't look at a function and understand what pieces it's made up of and kind of how those pieces are put together, you're going to have a really hard time taking derivatives of them, because taking derivatives, just like how with the product rule, you have to be able to tell which two things are being multiplied together, right? And so this is going to be the same idea. So if you have two functions, and I'm going to use two different input variables on this. We'll see later on why that is. Don't worry about it right now. Like, you can, when you have a function, you can use whatever input variable you want, right? You can call a function f of t is equal to t squared. You can call it f of w is equal to w squared. You can call it f of x is equal to x squared. Those are all the same function. So don't worry too much about the fact that I'm using a u here. We'll just see that it will help us to not have so many x's going on. I think it will actually make things more clear later on. So if f of u and g of x are two functions, let me say it this way, they can be composed to create a new function. And so that function can be written kind of two different ways. So you can either write it as f and then this little circle and g of x. And then an equivalent way of saying that is f and then g of x is on the inside. So basically what it means to compose two functions is to take one of the functions and plug it into the other one. So let's look at an example of this. So let's say that we have a function f of u is equal to the square root of u, and g of x is equal to 2x plus 3. So what would their composite function be? What would we get when we compose them? Well, f composed with g of x, which is the same thing as f of g of x, that's the function you get by taking the function g of x and plugging it into the function f of u. So what I'm going to do is, instead of writing this g of x right here, I'm going to write 2x plus 3, right? Because that's what g of x is. And so we have f of 2x plus 3. And then how does this work? Well, we know that the function f of u works by whatever's inside these parentheses, we're supposed to take the square root of it, right? If you were to plug in 5, you would say f of 5 is square root of 5. So same idea, f of 2x plus 3 is going to be equal to square root of 2x plus 3. And so this tells us that the function that we just got, h of x is equal to square root of 2x plus 3, that is what's called a composite function. Because how did we come up with this function? We didn't take two functions and multiply them together. We took two functions and plugged one of them into the other one. So I want to do a few more examples where now what we're going to be doing is starting with a composite function and trying to kind of work backwards to figure out what would be the inside and the outside function. So let me start a new page here. So for each of these functions, we're going to find functions f of u and g of x such that each of the functions that we are about to come up with are equal to f of g of x. So f is the outside function and g of x is the inside function. So with these, and let me actually just start by writing down the first example before I start talking more. So let's start with this one. Let's start with h of x is equal to e to the sine of x. So if you have trouble kind of visualizing what is the inner and the outer function in these, one thing I would really advise is trial and error. I think a lot of the time with math, people are really afraid to do trial and error because you just want to know how to get to the answer right away. I think if you skip the trial and error part, you kind of skip the part where you're actually figuring things out. So if we're looking at this and we're trying to figure out how could we break this down into two functions, the way I would think about it is, what are like the candidates here? Like, what are the different functions that we have? So I would look at this and say, okay, one of the functions that we have in this is definitely sine of x, right? That's going to be one of our two functions. And then what's the other function? Well, it's e to a power. So which one is on the inside and which one's on the outside? Well, I'm going to write it down correctly, but if you guessed it wrong, you could totally check whether your answer was right or not by just putting them back together and seeing if you get the right answer. So I'll show you what I mean by that. So what I would say here is, okay, let's say that our inner function is equal to sine of x. And let's say that our outer function is going to be f of, sorry, I want to, do it like this. F of u is equal to e to the u. So let's see what we would get if we were to compose these together. So f of g of x would be equal to f of sine of x, right? So I'm just going to put in what we said our inside function was. And then what do you get if you plug in sine of x into our function f, right? This is our function f. Well, you would get e to the sine of x, and that's exactly what we started with. So that's what I mean when I say trial and error. Just try something. Guess what it might be. If you tried g of x is equal to e to the x and f of u is equal to sine of u and you compose them, you would see that you would get the wrong answer. In that case, you would actually get sine of e to the x, and that's not our function. So really, truly just try these. And I would encourage you on these next ones, pause the video and try it yourself. Guess what you think the inside and outside function are, compose them together and see if you get the right thing. I think that's really the best way to ensure that you really have like an intuitive sense of what's going on here. So that was correct, and that tells us that our inside function was g of x is equal to sine of x, outside function was f of u is equal to e to the u. Okay, so another example, let's look at h of x is equal to 1 over x squared plus 1. So in this case, it looks like one of the functions we definitely have is x squared plus 1, right? That's one of the kind of building blocks of this function. But we also have, we have like 1 over something. So how could we write that as a function? Well, if we make our inside function be g of x is equal to x squared plus 1, that would mean that the outside function would need to be f of u is equal to 1 over u, right? Because then when we take the inside function and plug it into the outside function, we'll end up with 1 over our original inside function, which is what we want. So let's check that out. So if we put in our f of g of x, so f of g of x is supposed to be f of x squared plus 1. And then what does the function f tell us to do? It tells us that whatever is inside those parentheses, we're supposed to do 1 over that thing. So in this case, we would get 1 over x squared plus 1. And that is what we started with, so we're good. Okay, so we're going to do a couple more. So next one is actually the one that we started with at the beginning. So sine of x squared. So I think this one is actually easier than either of the other two that we just did because like the last two we did, I don't think you can really just look at it and say, oh, inside and outside function. This one, it's like literally the inside and the outside, right? So the inside function is going to be x squared. Let's see, what color do I want to use? I'll go back to that color I used on the first one. So our inside function is going to be g of x is equal to x squared. And then what does that leave for the outside function? Well, the outside function has to be h of u is equal to sine of u. Hopefully this color thing isn't too distracting. I'm just really trying to emphasize that this sort of visualizing what goes where in the function is the reason that I'm using these two different colors. And so let's test that we actually get the right thing. And sorry, I meant to write f. That's the letter we're using for the outside function. So if we try to compose these together, we get f of g of x is equal to f of x squared, right? Because that's what g of x is. And what is f of x squared? Well, the function f does sine of whatever is inside the parentheses. So in this case, we have sine of x squared. And that is what we started with. Okay, last example. It's going to look kind of similar to the last one, but it's different. Okay, so this is kind of a funny one because it requires that you remember what this notation means. So what does it mean when I write sine and then a little 2 and then x? That's just kind of a fancy way of saying sine of x squared. Right? Sine squared of x, it's basically just because if you want to write sine of x squared, it's basically so that you don't ever confuse it with this one, right? Like this one, if I were to write it this way, and maybe I got lazy with my parentheses, well, then it would start to look a lot like this one on the top. And we want to make sure that it is different and distinguishable. And so that's really, it's just a notational choice that people put the 2 up here instead of on the outside here. So once you rewrite it the second way, I think then it becomes a lot easier to see what is the inside and what is the outside function. So in this case, what is on the inside? Well, the inside is the sine of x part, right? The inside function is sine of x. And so what does that leave for the outside function? Well, if we think about what is the outside, or like what's happening to the sine of x, it's getting squared, right? So the outside function is going to be u squared. And so if we put these together, we take f of g of x is equal to, and then that means that instead of g of x, we can write sine of x, right? Because sine of x is what g of x is. And what is the function f supposed to do? Whatever is the input, you're supposed to take that and square it. So that means that this function would be sine of x squared, which is the same thing as sine squared of x. So we're good. Okay, so again, we haven't done any calculus yet, right? This part was all pre-calculus, just being able to compose functions or kind of vice versa, start with a function and figure out what are the pieces it's made up of. So now we're going to talk about like why are we talking about this? Because the goal is to figure out how do we take the derivatives of functions that look like these ones. Because right now we don't know how to take the derivatives of stuff like this. We only know how to take the derivatives of things that are combinations that are being either like added or subtracted or multiplied or divided. We don't know how to do these functions that are kind of one function plugged into another one. Okay, so I want to start by looking at an example to kind of give us some intuition about like why this derivative rule works the way it does. And then once we see that one example, then I'll give you kind of the official the official rule. It's called the chain rule, but we'll get there. So now we're talking about derivatives of composite functions. Okay, so let's look at an example, like I said. So let's look at the function h of x is equal to sine of 2x. So this is a composite function, right? Because it's not just sine of x, it's sine of 2x. So this is a composite function with its outer function being f of u is equal to sine of u, right? Because that's what's going on the outside of this function. And the inner function in this case is g of x is equal to 2x, because you're taking 2x and you're plugging it into sine of u. Okay, so if you had to guess what you think the derivative of sine of 2x might be, and, you know, like say, pretend it was last week and I just kind of told you to find the derivative of sine of 2x. Without thinking about it too much, you might guess that the derivative is cosine of 2x. Right? That kind of would make sense, right? Because we know the derivative of sine of x is cosine of x. So why wouldn't the derivative of sine of 2x be cosine of 2x? So I want to show you what the graphs of sine of 2x and cosine of 2x look like to kind of give us an idea of why it's not exactly the correct derivative. Okay, so right now I have pulled up here, this is the graph of sine of 2x. So just to compare it, so in green, the graph that's in green right now, and maybe let me make this bolder. Yeah. So the graph that's in green right now is the graph of regular sine of x. So what happens when you graph sine of 2x instead? Well, a couple things. I mean, the main thing that happens is the graph gets compressed horizontally, right? This number 2, that causes the graph to compress horizontally and become half as kind of wide as it originally was. It also increases the frequency of the wave so that you have more waves over the same time period. But if we think about what that does to the shape of the graph, it also causes the graph to get steeper, right? So if you look at the original sine graph, the very, very steepest that the slope of the original sine graph ever gets to be is 1. How do we know that? Well, we know that the derivative of sine of x is cosine of x, and the highest value that cosine of x ever reaches is 1. And so that tells us that the steepest derivative, and we went over this in that video last week where we estimated derivatives, we saw that the very steepest it ever gets is 1, and then -1 in the negative side. So if you take that graph and you compress it so that it's like twice as kind of tightly wound, well then, wouldn't you think that it would become twice as steep? So the very steepest that the graph in red gets, the sine of 2x, is actually 2 and -2. So let me pull up the graph of cosine of 2x. So cosine of 2x looks kind of the way you'd expect. It's like you took cosine of x and you smushed it horizontally. So in some ways, this looks like the correct derivative. So what makes me say that? Well, for example, so remember the red graph is our original function. At pi over 4, we have a horizontal tangent line. So the slope of the derivative, the slope of the tangent line is 0, so the derivative should equal 0. And then same thing with like here, right? The tangent line is horizontal, so the derivative should equal 0. So some parts of this derivative do look correct. However, what is not correct is that the steepest part of the graph is supposed to go, of the red graph, let me take this off for a second, the steepest part of the red graph, which actually happens right around here, this part of the graph, it should have a slope of 2. So that means that the derivative shouldn't just go to a height of 1, it should actually go up to a height of 2. Right? Does that make sense? So like, remember that the derivative's y values tell you the slopes of the tangent lines of the original function. So whatever is the very steepest your original function gets, the derivative function should have that as its height. And so that means that instead of having a maximum height of 1 and minimum height of -1, the derivative should really have a maximum height of 2 and a minimum height of -2. So what is a function that has the same shape as this one, but with those maximums and minimums? Well, if we make it instead 2 times cosine of 2x. So why is this the correct derivative? Well, again, we can see that in the places where the derivative should equal 0, it still equals 0. And that's what the 2x part kind of does. It kind of makes the graph line up the way it should. However, now it actually reaches a peak height of 2 and a minimum height of -2, which corresponds to the fact that the sine of 2x graph gets as steep as 2 or -2 as its slope. So the correct derivative for sine of 2x is actually 2 times cosine of 2x. So let's try to kind of make sense of that. So let me summarize first here so that you'll have it in the lecture notes, what we just said on the graph. We said that basically no. And basically the reason that we said that is that if we look at the graph of h of x is equal to sine of 2x, reaches a maximum steepness of 2 or -2 slope. So h prime of x should reach a maximum value of 2 and minimum value of -2. So the correct answer here is that h prime of x is equal to 2 times cosine of 2x. Okay, so let's try to make sense of like, where does this derivative come from? So basically there's 2 parts to this derivative. The first part is kind of the part that we guessed from the beginning. So why did we guess cosine of 2x? I mean, I guess I guessed it, but why did I guess that? Well, because we know that the derivative of sine in general is cosine. So I want to think of this as being our outer derivative. Basically, it's the derivative of the outside function. Right? Because our outside function, if we go back to how we broke this function down, our outside function was f of u is equal to sine of u. So the cosine part comes from that derivative. It comes from the derivative of sine. And then where does this 2 come from? Well, this is the derivative of the inside function, right? Because the derivative, or the inside function, in this case is 2x. And so what's the derivative of 2x? It's 2. And so that's where that part comes from. And so this is how it's going to work in general. And not, I think the example I gave you is an example where you can actually kind of visualize what's going on. That's not going to be the case for most functions. But what I want you to think about is the fact that both the inner and the outer function are contributing to the derivative. And so that's why you have to include both of them in the derivative the way that we did here. Okay, so now we're ready to write down officially what the chain rule says. So the chain rule is basically a generalization of what we just did in that last step. So the chain rule says that if you have a function h of x that is a composite function. So if you can write h of x as f of g of x is a composite function with inner function g of x and outer function f of u, then what is the derivative? Well, h prime of x is going to be equal to f prime of g of x, and I know this probably looks kind of confusing, but we'll make sense of it in a second, times g prime of x. So basically what's going on here is that this first part, this is the derivative of the outside function, right? F prime is, so f of u is our outer function. So this is the derivative of the outer function. And then why is there a g of x inside of it? Because basically whatever was the original input in your function, you just kind of leave there. And I'll show you that is exactly what happened in our last example in a second. So I'll just say it this way. So it's our derivative of our outer function evaluated at the inner function. So when I say evaluated, I basically mean that you're kind of leaving the inner function inside the derivative as it originally was in the function. And then what is g prime of x? That is going to just be the derivative of the inner function. So going up here, let's look at how this kind of fits. So the outside function was f of u is equal to sine of u, right? So the derivative of that would be f prime of u is equal to cosine of u. But there's no u here, right? Instead, we see this 2x being put there. And the reason that 2x is there is because that was our original inner function. So you kind of leave the original inner function inside, and then you also multiply by the derivative of the inside function. So this, I think it's really easy to kind of get lost in notation when you look at this because it looks very complicated. But think of this part just as saying, like, you kind of just leave the inside of the function as it is, and you just kind of take the derivative around the outsides. And then once you're done taking the derivative around the outsides, you multiply by the derivative of the inside function. Okay, so let's do some examples. So I want to actually use some of the examples that we did earlier. So we're going to do, I think, like 3 examples together, or 4 examples, and then I'll leave you with some to try on the worksheet as well. So let's do as a first example, h of x is equal to square root of 2x plus 3. So this was the like one of the very first examples we did. So let's try to first identify what is our inside and what is our outside function. We already did it earlier, but I still think it's good to do it again. So our inside function in this case is 2x plus 3. Maybe I'll use the same color as we did above to just really make this stand out. So we're using what orange for the inside function. So the inside function is 2x plus 3. And then what is the outside function? Well, it's f of u is equal to square root of u. And then another way to write that, because we're dealing with derivatives, we know that another way of writing the square root is to write that thing to the 1/2. Okay, so let's see how this derivative is going to play out. So in order to take the derivative, we're going to want to write down the derivatives of our inner and outer functions. So the derivative of the inner function, g prime of x, that's equal to 2x. And then what's the derivative of the outer function? Well, you would bring down, and maybe I'll stick with that orange. I was debating. So how would you take the derivative of the outer function? Well, we can use the power rule, right? So we're going to bring that 1/2 down. Oops, wrong color coordination. Bring the 1/2 down. And then we have u to the negative 1/2. So when we actually go and write down the chain rule, the one thing that we have to keep in mind is that we're not going to have a u in our answer, right? Everything should be in terms of x. And so what we actually want to put inside of this derivative, instead of the u, we want to put our original inside function. So not the derivative of the inside function, but just the original inside function. So that's what this going up, that's what our f prime of, sorry, I think my fingers are just sweaty because it's so hot today. I'm having trouble getting the screen to move. So up here, when we said f prime of g of x, that's what we mean. We mean you take the derivative, and then we're just going to stick our original function back in there. So what was our original inside function? It was 2x plus 3. So the derivative evaluated now at the inside function is 1/2, and then we have 2x plus 3 to the negative 1/2. And then maybe let's rewrite that a slightly nicer way. So another way of writing that would be 1 over 2 times the square root of 2x plus 3. Okay, so let's put these pieces together now. So what are the pieces that we actually need for our derivative? We're going to take f prime of g of x, so this is our kind of final version of that. And we're going to take g prime of x and we're going to multiply those two things together. So h prime of x is going to be equal to the outside derivative with the original inside function inside of it times the inside derivative. And in this case, that is going to be 1 over 2 times the square root of 2x plus 3 times the derivative of the inside function, which was, and sorry, I don't know why I wrote 2x. That should have been 2. My bad. Sorry about that. Times 2. And so now we can simplify this and we get 2 over 2 times the square root of 2x plus 3. And that can be written as 1 over the square root of 2x plus 3. So just to summarize again, because I know, and I feel like, so with the chain rule, I'm always very hesitant. So, we wrote all this stuff down here. Personally, when I'm taking a derivative using the chain rule, I would not write all of that out, and I'll kind of talk you through the way that I think about it. Personally, I think that everything that's written down on the right actually makes it seem more confusing than it actually is. But I have found that some students really need to write all of that down in order to get it. So that's why I do write it that way. But let me now just quickly mention how I would kind of think about the derivative. So I would just kind of look at this function and say, okay, so our inside function is 2x plus 3, and then our outside function is square root of x. So the first thing I'm going to do is I'm going to do the outer derivative. So I'm going to take the derivative of the kind of the outside, right? So what would that look like? It's going to be taking that, like if it was square root of x, it would be 1 over 2 root x, right? That's the derivative of square root of x. So I'm doing that same thing, but I'm just leaving the 2x plus 3 inside there. So it's kind of like you're doing the derivative around the 2x plus 3 and just kind of leaving it inside. And then this part here, oops, I changed my color up accidentally. This part here, this is the inner derivative. So on the next few examples I'm going to do it kind of both ways. I'm going to walk through the kind of long way of writing out all the details in case that's what works for you, but I'll also talk through kind of intuitively the way that I would think about it. And I think for a lot of people, once you've been doing this for a while, then I think you'll get to the point where you probably won't have to write everything out that we did on the right. Okay, so let's try h of x is equal to let's do e to the sine of x. This one was actually kind of a tricky one, I think. So if you remember earlier on when we did this one, we said that our inner function was sine of x. And our outer function was f of u is equal to e to the u. So what do we need in order to take this derivative? We need the inside derivative and the outside derivative. So the inside derivative is cosine of x. And the outside derivative, so first we can do it just with the u inside, and then we can go in and actually put in what our function is. So f prime of u is just equal to e to the u, right? Like the derivative of e to the x is e to the x. So the derivative of e to the u is e to the u. But now we want to go and put in our original function g of x into our derivative, kind of returning it to having its original input. So what is g of x? G of x is equal to sine of x. So that means that this is going to be e to the sine of x. So it's kind of funny, but when you're using the chain rule, the first part of your derivative is always going to be your original function if you had e to a power. Because when you take the outside derivative of e to a power, it's just going to kind of stay itself. So what is the derivative of this going to look like? We're going to multiply together these two things. So here's our outer derivative and here's our inner derivative. So we can put those two together and say it's going to be e to the sine of x times cosine of x. So how would I think about this? Well, I would just kind of think about, taking the derivative on the outside. Well, you're just kind of taking the derivative of e to a power. The derivative of e to the power is always just going to be e to that same power. So this is our outer derivative. And then we multiply by the derivative of the inside function. In this case, it was sine of x. And so this is our inner derivative. All right, I think we'll do two more. So let's do h of x is equal to 1 over x squared plus 1. So what we figured out for this one on the other page was that the inner function is x squared plus 1, and the outer function is 1 over u. Which, for the sake, so remember we're taking derivatives here, if you're taking the derivative of 1 over x or 1 over u, well, we probably want to rewrite it as u to the negative 1. Because that's what will enable us to take the derivative more easily. Okay, so what do we need for this derivative? We need the inside part of the derivative, so that's the derivative of x squared plus 1, that's just going to be 2x, right? Bring down the 2 in the power rule, and then the 1, derivative of 1 is 0. Okay, so now let's do the outside derivative. So f prime of u, using the power rule, now that we have rewritten it like this, u to the negative 1, it's going to equal to negative u to the negative 2. And another way of writing that would be negative 1 over u squared. So now we can go and put our original input back in. So we're not doing f prime of u, we're doing f prime of g of x. So what is f prime of g of x? Well, it's the same thing we got for f prime of u, but we're just going to put in our original g of x. So it's going to be g of x squared. So that's x squared plus 1 squared. So now we're going to put together our outer derivative, or sorry, that's our inner derivative, and our outer, I said it backwards, outer derivative and inner derivative, I was right the first time. We're going to put those two together. So the derivative of h of x is going to be equal to the outer part of the derivative, so that was negative 1 over x squared plus 1 squared. And then we multiply that with the inner derivative, which was 2x. So again, how would I kind of think of this without having to write all of that out? Well, if you know that the derivative of 1 over x is negative 1 over x squared, you're kind of just doing that same thing here, right? Like this is basically negative 1 over something squared. So you're kind of doing the derivative that you would do to 1 over x, but you're just doing that same behavior around the x squared plus 1 part. You're kind of leaving that as it is and just sort of doing the derivative around it, leaving it there. Kind of like pretending that x squared plus 1 is just x or just u, and doing the derivative and kind of treating it normally. So this is our outer derivative. And then after that, we have to multiply by the derivative of the inner function, and so that's this part. So the derivative of that part is here. And maybe as I'm talking through this, you don't feel like the two methods are that different from each other, and they really aren't. It's just kind of a more formal and a less formal way of doing it. All right, let's do just one more example. And we'll do more examples. Like I said, I would really recommend you try the ones on the worksheet, because I'm going to give you a couple. I'll basically put the ones that so we talked about sine of x squared and sine squared of x, and those are really important examples. So I'm not going to do them in the video. I'm going to ask you to try them yourself on the worksheet to kind of practice whether you understand what's going on here. And then we'll go over those examples in tomorrow's video, and also some other examples. Because I think this is probably the hardest thing that we've done so far in terms of derivatives. Okay, so this one's a little bit different in that we have now 3 times e to the x squared plus 1. So we'll see this a little bit more later this week, but we can use the chain rule together with like all of the other derivative rules that we've learned so far. So we know that when you're taking the derivative of a number times a function, you're allowed to just kind of let that number come along for the ride. And so we're basically just going to focus on the e to the x part. So we're going to kind of focus on this part, and then we'll just multiply the derivative by 3. So if you were just looking at this part, the inner function, so this is really similar to the first one we did here. So it's similar to, or actually the second one, e to the sine of x. So our inner function in this case is the exponent, right? It's x squared plus 5. And our outer function, again, is f of u is equal to e to the u. So we're not including the 3. I guess actually you could, but I think it's better practice to think about like any constant, just kind of leave it off to the side and focus on the rest of the function first. As long as the constant is just being multiplied with your function, you can just kind of sweep it to the side, put it back in at the end. Okay, so what is our what are our derivatives here? Well, the derivative of the inside function is going to be 2x. And then the derivative of the outside function, well, the derivative of e to the u is just e to the u again. And so what's going to happen is that when we go and plug in our original inside function, we're going to kind of see this repetition happen. So f prime of g of x means that we're now, instead of putting this u here, we're going to put our original inside function, so x squared plus 5. So when we go and put these together to write down our derivative, we're going to have this outer derivative times this inner derivative. And then we're also going to multiply it by 3. So we're going to have 3 times the outer derivative was e to the x squared plus 5. And then the inner derivative was 2x. So again, the way that I would kind of visualize this is that the e to the x squared plus 5, that's like you're just kind of doing the derivative of e to the something. You're kind of just leaving the x squared plus 5 there and doing the derivative kind of around it. If it was e to the w, the derivative would just be e to the w, right? So you're just kind of doing the derivative. You're kind of ignoring what this exponent actually is and just taking the derivative as though it was just a letter. And then after that, though, then you can no longer ignore this part in the next step. In the next step, you have to actually multiply by the derivative of that part. So again, this is our outer derivative, and this is our inner derivative. All right, so that's going to be it for today. Thank you all. I know that this stuff is definitely not easy, so stick with it. And I think this is really something where you need to practice it yourself to really kind of get a hang of it and be able to do it, without help. Like ideally, you want to get to the point where you can see a function like this and just kind of know what rule you have to use. And practice is really the way that you can get there. All right, thank you, and I will see you next time.